Okay, so as promised, I was going to make you guys a lecture, kind of going through some of the epoxide stuff here. Um, you'll have to pardon me. Usually, when I do a recording, I kind of plan out what I'm going to do ahead of time and do a little script stuff, but here we're kind of doing this on the fly, so if you'll notice a little bit more ums and uhs and some pauses and all that kind of stuff, just bear with me as we go through this. But anyway, so as we talked about in class, right, we got to the point where we figured out that we can create an epoxide from an alkene using MCPBA, right? MCPBA there. And to be honest, that's probably the most common way we have of doing, of forming an epoxide. There are, as with most organic transformations, a million different ways of doing this. There are different reagents and different conditions and all this kind of stuff, but MCPBA is a very, very, very common, um, very common way of doing this. There are other per acids also, right? Or per oxy acids, if you want to think about it, right? So other peroxy acids can do this also, but by far MCPBA is the most common one to do this. Okay. So I'm going to show you guys the mechanism, and then I'll tell you why we don't have to memorize it. Okay. So let's take a generic alkene, right? So we'll just do this here, right? So we have our cyclohexene, and I'm just leafing through to find my notes here, right? So we have an alkene, and let's just zoom in and simplify some stuff for us. So I will just abbreviate, let's do a different color here, black, right? I will abbreviate this part of the MCPBA as my R there. Okay, so when you guys see R for now, I'm just talking about that, the chlorobenzene part. All right, so there's my this. Now you guys, some of you guys might be able to see where this is going already. I arranged it in that way because this is going to kind of, I don't know if we'll say make the most sense, but it'll give us where we need to get to, right? All right. So here we go. Pi bond swings out, hits that oxygen, okay? We make a bond. We will break a bond. Let's change colors. We'll make a bond, we'll break a bond. Okay. We'll follow up with this one here. Okay. Okay. And I'm running out of colors, so we'll just have to go back over, and then we will do that. All right. Now, I'll zoom in here. I'll kind of label it. All right, I did this one first, right? Then we broke a bond here, right? So that one's number 2. That's what I did number 3. That's what I did number 4. That's what I did number 5. Sorry, that should have been number 5. I did this one at number 6 here. Then I did this one at number 7. Okay. So in red, the pi bond attacks the oxygen, right? And the oxygen-oxygen bond breaks while oxygen-carbon double bond forms, while a carbon-oxygen double bond breaks, while an oxygen grabs a hydrogen, while a hydrogen-oxygen bond breaks, and an oxygen-carbon bond forms. Okay. This is pretty complex, but if you pause, take a minute, and the reason why I drew all these arrows is because it's a little bit easier if you guys deconstruct it one at a time. If you take a look online, right, there's different amounts of arrows that are drawn with these. It's not that one is necessarily right or wrong. It's that some of these steps can be condensed down, right? Some of these can be condensed down into individual parts. And just for argument's sake, right, let's see if I can simplify some of these here. So let me erase some stuff, right? So let's simplify some arrows to see how things can work, okay? So if you take a look online, right, we could do that, right? And this, and then this is where it gets a bit different, right? We could draw this coming down here, right? Oops, I missed one set of arrows. This still has to get grabbed by that there, so sorry, forgot about that. So red arrow then, right, 1, 2, right, in black, 3 here, 4 there, and then 5 here. Okay. So if you take a look online, that's how most of it is depicted. How's the other one there different, or we're just kind of combining some steps together? I guess from a simplistic standpoint, either one of these is going to be fine. You know, one's just maybe a little bit more elegant than the other, but the one with the more arrows there will kind of give you a better view of how the electrons are flowing, maybe. But you know, none of these are going to, right? That's not really the important part, right? What this does say is that this all happens on one face, though, right? This is something that has to happen on the same face. So if you take a look at arrows 1 and 7 or 1 and 5, right? The pi bond and that incoming oxygen there, right? That has to happen on the same side. But if we back away from the mechanism for just a minute and just think about this logically for a second, right? Right? That's the product that we expect along with, right, this guy here, right? We can add it to either face. It doesn't really make sense for us to be able to make an epoxide like this, right? Where one's wedged and one's dashed. If you think about this and you try and build the model, right? If you try and build the model for this, right, it just, the stuff doesn't come together like that, right? The epoxide is going to be added to one face of that pi bond, right? The top or the bottom face, whichever one it might be. Okay? Cool. So let's come up with a different way of making an epoxide. Well, I guess I have to apologize because I lied to you guys. Because I said I wouldn't teach you guys anything new in this chapter, so I'm sorry. This is something you guys hadn't seen before, so apologies. I didn't mean to lie to you guys like that. But now let's go back to something that you guys have known before, and something that you guys can already give me the answer to. Right. Start with Mr. Alkene. Okay. Okay. Now pause it, right? So pause this video and see if you can come up with the product of this reaction, right? So just like we did in class, right? We kind of did these little checks along the way there. See if you guys can come up with that product. All right, if you're back, hopefully you came up with this, right? Your halo-hydron reaction, right? Your halo-hydron. And remember, you'll make a set of enantiomers with that too, right? We'll just keep it simple for now. Now, if we take our halo-hydron and we put it under aqueous hydroxide or basic conditions, what we end up forming is our epoxide. Let me draw that a little bit nicer. For some reason, I really struggle with drawing epoxides. I can't give you guys a good explanation as to why that is. Say, right? So we're turning a halohydrin into an epoxide. Can you guys maybe propose a mechanism, right? Can you guys maybe propose a mechanism or a series of steps, right? So pause here, right? See if you guys can come up with a mechanism to get to this. And I'm going to go ahead and give you a hint, right? You guys already know the mechanism for this. You guys already know the steps, right? All you guys have to do is stop and think and apply what you guys already know to get to that mechanism. Now, I'm going to have to pause the video here for just a minute, so you'll pardon kind of the other kind of screens popping up. I will see you guys in just a minute, though, as soon as I get back. All right, so we are back. So did you come up with a mechanism for this? So let's see if we can figure out. Well, we got water around. That's going to be our solvent and our proton shuttle, that kind of stuff. And then we have our base around here too, right? And so that's the thing that we kind of have to pay attention to, right? So we're under basic conditions. Now, truth be told, right, there's a lot of different reactions that can happen here. And so just keep that in mind, right? But here, if we're under basic conditions, right, we're on the hunt for something acidic. And really the only acidic thing we have here is that hydrogen attached to that alcohol there, right? So let's deprotonate that. Okay. Can you guys draw the arrows to do that? Let's draw the arrows real quick then. Let's not be lazy. Sorry, not lazy. Let's not be time inefficient. Ugh. I'm being a dum-dum. All right, here we go. And we had hydroxide around, right? So there's our hydroxide. Nice. Okie dokie. So acid-base reaction, easy peasy, right? So now we're down here. Cool. So what do we have now, right? What we have now is an oxygen with a negative charge. Okay, well, we know a lot about oxygens with negative charges, right? They're strong bases, they're good nucleophiles, they do eliminations, they do substitutions, they can, we've done a million different reactions with them at this point, right? But we know we want to get to the epoxide, right? So let me give you guys a visual hint here. I'm going to mark that as yellow. Okay, so we'll just mark that as yellow. Okay, cool. And then we'll mark this as green, right? We'll mark this as green. Yellow, green. Right. Okay, can you guys see what might happen here then? Boom, 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 boom. We do this kind of very weird mechanism which we've never seen before. Just kidding. What is that? Right? An oxygen just attacks from the opposite side of a bromine leaving, right? So this is just an SN2 reaction here. Okay? Now, this has to be done in a special arrangement, in a special way, with the things on the opposite side from each other, right? There are some conditions for this, right? And then we end up generating that epoxide there at the end, right? But this is another way that we can form epoxides from a halohydrin. Now, there's a couple of problems with this, and hopefully you can see what the issues are. If I use sodium hydroxide, how selective is sodium hydroxide? The answer is it's not. Is it a strong enough base to deprotonate that alcohol? Yes, it is. Yeah, but it's not that strong a base, right? Alcohols aren't that acidic, right? Truth be told, we should be using some other bases to do this, because not only could the hydroxide deprotonate that alcohol eventually, maybe to some extent, right? But it could also, right, maybe right? Just simply do an SN2 reaction here, right? That's a secondary leaving group, right? It's a pretty good leaving group. We got a bunch of hydroxide around. We got a bunch of water around, right? We could do an SN1 maybe, right? It'd be kind of slow, right? But this isn't a very clean reaction. But we do need some kind of base around, right? So we could use some bulkier bases to get this done. Now we could use something like T-butoxide, maybe, right? We could use something like T-butoxide, maybe, right? We could use something like sodium hydride, potentially, right? Or lithium, butyl lithium, which we'll talk about in just a little bit. So really, what we should say with this is we need some kind of base, right? We need some kind of base around. And the bulkier it is, the better it's going to be at doing the acid-base reaction with that alcohol to help this reaction go along, right? So I hope that all made sense. But we really needed some kind of base to set up our deprotonated alcohol here, which can then do an internal, right? We do an internal SN2 there. So this is an intramolecular reaction. Most of the stuff we've been doing is intermolecular, right? So intermolecular is between different molecules. Intramolecular is within itself, right? Now we've seen some of these intramolecular reactions, and we'll see a couple more as we go along, so just something to start paying attention to. Generally speaking, right, so I'm speaking in generalities. Generally speaking, intramolecular reactions are faster than intermolecular reactions. And if you stop and think about that for a minute, right, it might make sense. Right? Because remember, for an intermolecular reaction to happen, we have to have two molecules come together in the right direction, with the right speed, at the right trajectory, at the right time, right? And then the reaction can happen. But intramolecular reactions, right, just happen within themselves, right? There's not all these conditions that have to get met, or I should say there's not nearly as many conditions that have to get met. Okay? So something to think about there. All right. So I can hear you on the other side of this screen thinking, so what? All right, so we've made an epoxide. Big deal. What are we going to do with those? Well, let's take a look at how it, what we could potentially do with an epoxide here, right? This falls under the broad aegis of ring openings. All right, so ring opening of epoxides. So guess what ring opening of epoxide means? It means we're going to open the ring, right? Shocking. I know. We'll say, well, wait a minute. Why do we want to do that? What's the point, right? There's two broad ways we can open an epoxide, right? Under acidic conditions and under basic conditions. I was debating on how to do this, right? Since I have to do this by recording, I'm going to go ahead and give you the punchline here, right? If I change from acidic to basic conditions, we're going to change how the ring behaves and how the ring opens. Under acidic conditions, okay, under acidic conditions, the ring opening of epoxide, right, follows, whoops, I meant to do that in purple, excuse me, the sumo principles. Can't spell. How embarrassing. Now it's, right, the sumo principles. So you got to go back and think about your sumo mechanism. And how did that behave? Well, go back and review your sumo mechanisms, right? And you'll see that it behaves kind of like an SN1, right? Leaving behind a partial positive charge on the more stable carbon, which is SN1-like, or SN1-ish, right? So sumo mechanisms follow the SN1-ish principles. Basic conditions are going to follow the SN2-ish principles. Okay? That's really it. So I could just end all this recording here and we'd be done pretty much for the chapter, right? But we're going to kind of break this down and see what happens with it, right? So let's see how long I've been chatting with you guys here. About 20 minutes. Okay. I wanted to say I only want to do a 30-minute recording for you guys. So let's see what we can get done in 10 minutes and we'll pick it up in class, right? So let's talk about the easier of these two, right? Let's talk about what happens under basic conditions. Well, I shouldn't say easy, but I should say maybe the simpler of the two, the more straightforward of the two. Okay, so let's take an epoxide and put it under basic conditions, right? Here is Mr. Epoxide. Isn't he adorable? All right, we're going to do this guy here. Okay. All right. We're going to use some brand new reagents, which you guys have never seen before, right? Wow. A conjugate acid-base pair. An extremely powerful base, right? There's our buddy Ethoxide, right? Ethoxide. Seen that a million billion times at this point, right? What has it done for us in the past? Eliminations, substitutions, right? So let's take a look at this mechanism then. Now what we have to understand, oops, let me draw it a little bit better. What we have to understand about epoxides is that there's a lot of ring strain, okay? I don't want to use purple, right? There's a lot of ring strain. So if you remember way back in the day when life was easier, back in Orgo 1, well, Gen Chem 1 too, that was easier, right? But Orgo 1, right, we talked about the different sizes of rings, right? Cyclopropane, cyclobutane, cyclopentane, cyclohexane, we talked about a lot, right? The angles inside of an epoxide, right, are closer to about 60 degrees, but they're all sp3 hybridized. They really want to be closer to, 109, right? It wants to be closer to tetrahedral angles. So there's a lot of ring strain that's forcing it to stay as a three-membered ring. So it's pretty easy to open an epoxide. In fact, if you guys ever use super glue, right, you might have used a form of epoxide in there that kind of reacts with everything in the air, right, and starts a polymerization reaction, these kind of things, right? So we do see epoxides used in day-to-day life, right? But ring strain is what causes this to happen. So here is how this mechanism looks. Under basic conditions, the incoming base is going to attack that carbon specifically right there, right? Why? Well, what does this mechanism kind of look like? I'm going to give you a subtle hint. Okay, it's going to be very subtle. And let's see if we can pick up on it. Got it. Right, this is an SN2-like reaction, right? We're going to hit from the opposite side that something is leaving, okay? So if we follow along with this, right, let me try and draw this as best I can to kind of maintain, right? Good. You guys see that? Now we need to finish things up. We want to fix that oxygen right there. So usually, this is what we do last. Okay. The last thing you'll see is an acid workup. And whenever you see an acid workup in organic chemistry, basically we're going through and protonating things. Okay, so our acid workup is going to end up just taking our negative there, right? And protonating that so that we end up with an alcohol. Interesting, right? So our acid workup is how we get that there. So what did we end up making? Well, we ended up making an ether, right? We ended up making an ether and an alcohol right there. So we have two functional groups now, right? Starting from an epoxide. Now there's something important at work here too. Remember, this is SN2-ish, which means the incoming group is coming from the opposite side of the leaving group there. I mean, leaving group in the sense of the group that is, that breaks the bond there. That means that this is an anti-addition. Okay, that's important. The incoming group comes in from the opposite side of the epoxide ring. Now this isn't too much of a surprise, right? Because remember, we're following some of these sumo principles also, right? And we're following, right, an SN2 type mechanism here. So we're going to see some overlap between these conditions also. We're going to see some similarities between acidic and basic conditions. And one of them is that we have anti-addition in both cases for somewhat different reasons. So did you catch that? Right? We're going to have anti-addition in both cases, but for somewhat different reasons. Cool. So let's do a quick example, and I think then we'll call it here. Okay. Why would we want to do this? Okay. Let's take our alkene. We will make an epoxide. Right? We'll just say that is the one that we end up making there. And then if we put this under basic conditions, right, let's just put in some aqueous hydroxide. Okay. What we'll end up making then is this. Okay. And then we will probably have to come back and fix this all up with some acid workup. Okay. And then we will end up with so this is an anti, right, diol. Now that's kind of weird sounding. I'm not anti in the sense of against, right? Remember previously, when we change colors here, we had the syn diol formation, right? Syn diols, right? Right now we're talking about anti, right? So on the opposite sides. We currently did not have a way of making an anti-diol, but now we can, but we have to go through an epoxide here, right? So the epoxide, going through the epoxide, opening it under acidic or basic conditions, right? We'll look at it under acidic conditions in just a minute, but opening an epoxide will lead to an anti, right? Or trans in this case also, trans diol. Sound good? A little bit of homework for you. Do you guys remember how to do the syn diol there? That'd be something to think about. Okay, I think this is a good place to pause the video for now. We'll pick this up with the acidic conditions in class. But go through this, make sure you kind of look through it in the book too, and I will see you guys on Monday there.